For investigating diffusion, the goal of our experiment was to determine in which solutions the 2PS beads would diffuse the fastest. We're going to base our conclusions on the relationship between the density of the solution and the rate of diffusion of the beads, which we're going to determine using the diffusion constant. We are predicting that the more dense the solution is, the slower the beads are going to diffuse. For our methods, we set up an experiment with beads diffusing through various liquids. Our control was the same size of beads, which was the 2PS, and our independent variable was the liquids. We used water, soap, and corn syrup. The beads were followed using a microscope in order to determine the movement within the fluid, and the video we then placed into Tracker to track the motion of a single bead at any given time. Our models consist of a system schema, which we included the bead, the fluid, and the earth. The earth has gravitational effect on both the bead and the fluid, and then the bead and the fluid have contact. For the force body diagram, there is a gravitational force pulling down on it, and there is some force going upward that is balancing the gravitational force. And there is also a force whenever the bead collides with the solution molecules. So all of the orange dotted lines are the forces based on the collisions in various directions.
The velocity versus time graphs of the beads and various fluids from Tracker. These graphs show that the speed at which the beads are moving in the three liquids, corn syrup, dish soap, and water. The first part of a prediction is shown here, that the beads are moving faster in water than they are in corn syrup. However, we can't tell from these graphs whether this movement is diffusion or coherent.
In order to determine whether this is random motion or coherent motion, we're going to plot the log of x, or displacement, versus the log of time. We know that acceleration is proportional to t squared, constant velocity is proportional to t, and random motion is proportional to the square root of t. So if we plot the logs of these equations, we'll get a linear line with the slope of 2 for a constant acceleration, a linear line with the slope of 1 for constant velocity, and a linear line with the slope of 1/2 for random motion. We then took our data and did the same thing, graphing log x versus log t, and we got the following slopes. For corn syrup, we got 1.6. For soap, we got 0.27, and for water, we got 0.26. This shows that this activity is not strictly coherent or random motion because there are outside forces involved and it's not a perfect system, so it's going to be a degree of randomness or coherentness. However, even though our data doesn't show that this is strictly random motion, we know by the nature of the activity that this should be mostly diffusion. So from here, we can use our data to calculate the diffusion constants for each liquid.
The calculation section, we calculated the diffusion constant using the 2D equation. We used the graphs from Tracker and found 2 points for each liquid and found the change in time and the change in distance to plug into the equation. And for water, we got a diffusion constant of 2,416. For corn syrup, it was 755. And for soap, we got a diffusion constant of 1,427.
Based on our initial prediction, the results section has 2 parts, the rate of motion and then determining whether that motion is random or coherent. The diffusion constant for water was the highest and for corn syrup the lowest. The diffusion constant is the rate at which it diffuses, so that will show us the velocities of the beads. This follows the prediction based on the densities. Regarding the random versus coherent motion, it should be linear slope of 0.5, but it is not true random motion in this situation. It's actually a mix of both random and coherent motion.
Some of the limitations of our experiment include the inability to track the motion of the bead in 3D, so the depth of the bead is unaccounted for, and our data is not entirely conclusive. Also, due to outside forces such as breeze and currents in the fluid, our motion is not completely random. This implies that our diffusion constants and log graphs are not accurate.